This video here is meant to be an extension of the previous one on Faraday's law, but the focus here will be to take a look at how electric generators work. So of course Faraday's law is stated right here sort of as a mathematical rendition of Lenz's law, which says that you can get volts out. That's what this induced EMF is, volts out here, if you have a changing magnetic flux. So the time derivative here is directly mapped to the word change in Lenz's law, and the minus sign is directly mapped to opposes in there. So you have it all together. It's changing magnetic flux, and there's the opposed. But the point is that if you can have a non-zero time derivative of your magnetic flux, you'll get volts out. That's exactly what generators do. They produce volts for us so we can run our houses and our electrical devices. So the question becomes, well, what do I need to get that volts to appear? Well, three ways, as we looked at in the Faraday's law video, previous one. You can have a changing magnetic field. You can have a changing area of a loop in a magnetic field, and you can have a changing angle in there. So what we're going to declare in this discussion on generators, we're going to say the magnetic field is constant. So this isn't going to ever help us. It's the time derivative of a constant zero, so if B is constant, dB dt is going to be zero. It's not going to help us. The changing area with respect to time is really just reserved for sort of contrived textbook problems. We're not going to sort of worry too much about a changing area here. But we are going to be concerned ourselves with what happens if the angle between the magnetic field and the area changes, and that's the d theta dt. Now the reason why I have these three cases here, because if you imagine taking a derivative of this with respect to time, the product rule from calculus says it will be the time derivative of this times these other two things, plus the time derivative of this times these two things, plus the time derivative of this times those two things. Those are the three combinations in there. But in this case here, we're going to focus on the angle changing. So to do that, let's just explicitly say that theta is something like omega times t. So let's just make theta some explicit function of time here, and remember that omega here is some amount of radians per second that the loop spins through, so many radians per second. So it's almost like saying, yeah, you can have the position of an object here, but if you say the position is velocity times time, suddenly you can move and it'll be an explicit function of time. So we'll just do the same thing here. And if I do that, so if I put theta is equal to omega t in here, then my magnetic flux equation becomes B times A times the cosine of omega t. And this is kind of, getting to hint about how generators work now, because if I say I made a plot of this, it's just a cosine function now. So if I just plug that in like this, and I plotted the magnetic flux as a function of time, now that I have that explicit time dependence in there, it just behaves like a cosine. So I'll do something like this. My graph's pretty awful, but it behaves like a cosine, and what I remember about cosines is at zero, they're sort of one or maximum like that, and they go from there. So it'll look like this. And the point is as follows here. Do I have a magnetic flux that is changing with time now? Yes or no? Is it changing with time? No matter how messy my sketch is this changing with time? And the answer to the question would be yes. At one moment it's up, at 1 minute it's zero, next moment it's down, then it's up. As time goes on, this thing's going up and down, up and down, up and down. And remember, that's what I need in order to get volts out. I need a time derivative of magnetic flux here. And it looks like I have it here. By making the angle change, I have it. So what does it mean to make an angle change? Well, before we sort of do that, let's just go ahead and take that time derivative and see what we get. So in other words, I'm taking the derivative of this function here. Now remember, B and A are constant, B times A. And the time derivative of cosine is minus sine. Now that you have to take the derivative of the inside also, so the derivative of omega t is just omega. So in other words, the d flux dt, the non-zero item I need to get a voltage, according to Faraday's law, is minus omega, the rotational rate, times the magnetic field, times the area, times the sine of omega t. So maybe you still don't see where generators come from, but look, here's my d phi b dt. It's an explicit function of time itself. Looks like it can or can be zero, and sometimes, but it looks like I am getting values out of this sucker here. And so this quantity right here, d phi flux dt, is exactly what's needed over here to get a voltage out. That's the key thing about how generators work here. The faster I spin it, the larger d phi dt is going to be, the more voltage I'll get. The larger magnetic field I can possibly build my system around, the larger d phi b dt is going to be, the more voltage I get. The larger area I can possibly get in the magnetic field, the larger d phi b dt is going to be, the larger voltage I'm going to get. Now we have the sine system sitting in here, remember, which is a number that goes between 0 and 1, minus 1 and 1. Sometimes it'll be 0, sometimes it won't be, but it has some nice maximum in there, so it looks like I am going to get sort of a sinusoidal changing magnetic flux with respect to time, which will mean I'll also get a sinusoidal electromotive force or sinusoidal volts coming out. So if I put all this together here, and sort of made a plot now of the electromotive force here, which remember is really d phi b dt as a function of time. It'll behave like a sine, but looks like behave like a sine. I was going to say it's going to be upside down because of this minus sign, but remember that Faraday's law also has a minus sign in there, so that cancels. So I'm going to get a sine wave out. I'm going to get a sine wave, and I know sine waves look like this. They're out of phase with a cosine like this. They start at 0, and of course the amplitude of the sine wave, either the maximum up here or the maximum down there, is omega BA. So the maximum amplitude of my induced EMF is going to be proportional. It's going to be equal to my spin speed times my magnetic field strength times the area that's in the loop. So I will get an EMF out of this. Pictorially, it looks like this. We need a magnetic field, and we need an area, and we need that thing to spin. So if I make a big magnetic field region like this, and this is what I sort of stated on the onset of this video here, this is going to be a constant for us here. It's not going to change at all. No dBdt. And what I'm going to do next, I'm just going to put a loop in this thing. Here's my loop like this, and I'm going to put it on some axes like this so it can spin. And I don't know what the holders will look like. I'm sure everyone watching this is a better engineer than I am, so you can sort of put them on some holders like this and like this. There we go. So you can imagine this thing can spin now. It's almost like a little DC electric motor. But now here's the thing. By spinning, I mean the loop is going to sit here in this magnetic field. Remember, these red dots here are your B field. The loop is going to sit here in this magnetic field, and it can spin. It can go like this. It can start spinning like that. That's the nature. That's why I put it on these two holders like this, so it can spin. Now you have to think a minute here. How fast is it spinning? Well, that's my omega right there. That's my spin speed. So it's spinning around this axis like this with a speed omega like that. And if you think about what's happening here, when the loop is sitting in a position like this, the normal to the B field is straight out like that. And when it goes up like this, the normal is at 90 degrees and the normal is the other way. So I am changing the angle of the area relative to the B field, and that's that theta changing. That in the cosine theta, which is in the magnetic flux. Hopefully you can see how theta is changing in there. And so if I sort of get this thing rotating like this, it starts going like this, that's the omega, there's the B, and here's the area right here that's in the magnetic field. Now sometimes, like when it's an orientation like this, I'm getting maximal sort of flux through there. Other times the flux is like this. Other times the flux goes maximum, or some places in between there. But what I'm most concerned about for my voltage is how is that flux changing? The d phi bt dt. And that's exactly what you sort of look at by looking at the equation you wrote in the previous screen. But this, in a nutshell, is how an AC generator works. You just take a coil like this and get it to rotate in a magnetic field like that. And if you were able to monitor the voltage, sort of say these things are all made out of metal and stuff, and where these things are contacting right here, the currents that produced can come out, and you can sort of get a measure of voltage right here. And suppose you ran it through a resistor down here like this, or something that consumed a little bit of that power, and then across the resistor here, you put your voltmeter here. The question is, what is the voltmeter going to read as this thing spins? And what this voltmeter is going to read is exactly that induced EMF that we sort of had earlier on an early portion of the video. The EMF is a function of time. When you get this sinusoidal EMF coming out, up and down and up and down, so the voltmeter will read sort of a sine wave as this thing spins and spins and spins and spins and spins, and that's exactly what an AC generator is. So an AC generator, and letting that theta change relative to everything in the problem, relative to the B, relative to the A, is just really a nice example of a direct application of Faraday's law about how just spinning a loop in a magnetic field is where electricity sort of comes from. And just two more things on that. Where does the spinning come from again? And we've had this a few times in previous videos here, but of course the nature of at least fossil fuel-based power plants is you have a hot fire here. You have something hot. And remember where the hotness can come from here. It can be nuclear, it can be natural gas, or it can be coal. Those are sort of the most common heating elements used in power plants. So they're exhaustible and they're dirty and they have all these sorts of problems and stuff, but nevertheless, it is what it is. And what you do is you'll just put that tank, you put that hotness, you're a tank of water. There's water like this here, so you put a bunch of water in here, and here's the water, and of course the hotness boils the water and you get this steam coming out. But you've left a little hole in the side of your tank over here where some of the steam can escape, a lot like your tea kettle. And if this steam can escape, then what you can route the steam on is to a little paddle wheel like this. And so as the steam sort of water molecules hit this paddle, maybe the paddle wheel is going to start turning this way. And this turning here is your omega. This paddle wheel turning is the omega, because what you could do instead of drawing, well, you can leave the paddle wheel like that, but maybe the paddles, and let me just draw it a slightly different way. You're going to need the paddles on there so the steam molecules can hit them, but maybe in the interior here is where I'll draw the loop like this or something, so the loop can start to spin, and as the loop spins, we can immerse the entire thing in a magnetic field. Again, I'm losing the perspective with the two-dimensional drawing here, but maybe I'll have just immerse the entire paddle wheel in a magnetic field. And if I can engineer some sort of way of getting this loop that's being spun by the steam to change its theta in terms of that omega in Faraday's law, then as long as I have the fire, as long as I have the steam, as long as this paddle wheel turns here, this omega here will give me my induced EMF, my voltage out. And so just those little loops that I drew on that one-turn generator on in the previous part of the video here, those little wires that were coming out like this, these would be the wires here that then you would just sort of take down here and then go ahead and connect to the power lines. Connecting to those power lines like this and just route this out. It's not quite this simple. There's some processing and so on and so forth, but that's sort of in a nutshell what's inside the powerhouse, where that voltage comes from. So that voltage starts pushing current down these wires. And of course it's sinusoidal, as we saw here, so 1 minute the current in these wires is going to be to the left, the other minute is going to be to the right, but that's the name of the game for generators. Get that loop to spin by virtue of escaping high pressure steam, and as long as it spins, you have an omega, which makes the theta, the angle between the loop and the magnetic field change, and your EMF comes out. And the other thing that we sort of glossed over is there is this version of Faraday's law here, the change in flux with respect to time. You don't always have to build your loops out of one loop. You can have many loops, which is commonly has a symbol N in there. So whatever one loop does, two loops will be sort of twice the magnification in there. So instead of just putting one loop in a magnetic field like this, why can't you just take the wire and just spin it around thousands of times like that? So the induced EMF you'd get out would be 1,000 times the amount. Not a really strong contributing factor, it's just a linear factor, just one for one in there. But nevertheless, Faraday's law does have a number of turns parameter in front of it in some cases there. So there you go. There's a ramification of Faraday's law and how that changing angle can produce an EMF.